Okay, so our topic today is EPR paradox and quantum entanglement. The introduction for EPR paradox is it is proposed in 1935 by Albert Einstein, Boris Podolsky, and Nathan Rosen. Questions if quantum mechanics provides a complete description of reality. It also highlights strange predictions about the behavior of entangled particles. For quantum entanglement, it is a phenomenon where two or more particles become linked and instantaneously affect each other, regardless of distance. The state of one particle is directly related to the state of other, even if they are far apart. It's also referred to as spooky action at a distance by Einstein.
For EPR paradox, it was proposed by Einstein, Podolsky, and Rosen in 1935. That's why it was called EPR, means Einstein, Podolsky, and Rosen. For the main idea, EPR aimed to demonstrate that quantum mechanics might be incomplete by focusing on the concept of entanglement. They also argued that if quantum mechanics were complete, it would provide a full description of a physical reality without the need for spooky action at a distance. For the key terms, entanglement. It is a quantum phenomenon where particles become interconnected such that the state of one instantly influence the state of the other, regardless of the distance separating between the particles. For local realism, it means the belief that physical properties of particle exist independently of measurement and that information cannot travel faster than the speed of light.
So for this part, I'll be talking about the type of experiment, what is EPR paradox. So for the setup for the experiment is firstly creating the entangled particles. This is about consider a source that produces a pair of entangled particles A and B. These particles are created with properties such as perfectly correlated. For an example, if a particle has a spin up, particle B will have spin down. Next, the step is separating the particles. After the creation, particles A are sent in opposite direction to two distant locations where Alice has particle A and Bob has particle B. The separation between Alice and Bob is significant enough to prevent any direct communication between them during the measurement. So for this experiment process, firstly the state before the measurement. In the quantum mechanical framework with unit measurement is taken, both particles A and B exist in a superposition of states. This means neither particle has a definite spin until it measured. Measuring particle A. Alice measures the spin of particle A and finds the spin up to be spin up. Upon measurement, the wave function collapses and particle to a state instantaneously determined to be a spin down. For the measuring particle B, Bob, who is far away from Alice, measure the spin of particle B. He will always find particle B to be spin down if Alice measured particle A to be spin up. If Alice had found spin down, Bob would measure spin up. So for the outcome, instantaneous determination. The critical outcome is that Alice's measurement immediately determines Bob's measurement result, despite the distance between them. This suggests an instantaneous connection of influence which contains the principle that nothing can travel faster than light. Second, challenges to local realism. Local realism posits that physical properties are determined before measurement. Realism and that no influence that can travel faster than speed of light locality. The interpreters challenge this motion by showing that motion one particle seems to be instantaneously affect the other particle's state no matter the distance separating them. Quantum entanglement. So for this definition for this quantum entanglement is two or more particles become entangled when their quantum states are independent. The interconnection changes to one particle state instantly affect the state of the other no matter how far apart they are. For the properties, superposition. Each particle exists in multiple states simultaneously until it measured. Measurement impact. Measurement one particularly collapse the integral system into a definite state, instantly determining the state of other particle. For an example, for the photon pace, when photons are entangled, be measuring the polarization of one photon instantly determine the polarization of the other. Electrons, for the example of electron spins, entangled electrons exhibit correlated spins even if separated by large distance. Non-locality for the definition of this non-locality is instantaneous state correlation. The integral particles are correlated instantly regardless of the distance between them. For the key concept, non-classical communication. The correlations happen faster than speed of light, implying no classical signal is exchanged. EPR paradox. Einstein, Podolsky, and Rosen EPR project entanglement challenges the competence of quantum mechanics, calling if spooky relation of distance.
Bell's theorem. In 1964, physicist John Bell formulated a theorem that provided a way to test the validity of the EPR paradox and the existence of hidden variable. Bell derived inequalities known as Bell inequalities that must be satisfied if local hidden variable theories, the idea that particles have pre-existing properties determined by hidden variable, were correct. Last, provide a testable distinction between quantum mechanics and local hidden variable theories through Bell inequalities. Okay, next is experimental evidence. Consistently violate Bell inequalities, supporting the non-local nature of quantum mechanics and challenging classical notion of locality and realism. Aspect experiment 1981 until 1982. Alain Aspect and his team performed a series of experiments that improved upon yearly tests by closing certain loopholes. Second, this experiment involved measuring polarization collation of intelligent photon and demonstrate clear violation of Bell inequalities. Last, aspect works provide strong evidence against local hidden variable theories and in favor of quantum mechanics.
So hi, my name is Muhammad Iqbal bin Azri and I want to present to you about quantum entanglement. So what is quantum entanglement? Quantum entanglement is a phenomenon in physics that arises when particles are formed, interact or share space in pairs or groups in a way that makes it impossible to characterize the quantum state of any one particle without also describing the states of the others. The states of the particles stay connected even at great distances between them. So for the first part of quantum entanglement is quantum computing. Quantum computing consists of superposition and entanglement and quantum algorithms. For superposition and entanglement, unlike conventional bits, quantum bits are capable of existing in several states concurrently. Qubits may be occupied by entanglement in a way that makes it irrelevant how far apart they are from one another. The state of one qubit instantaneously affects the state of the other. For quantum algorithms, because of entanglement, algorithms such as Grover's algorithm for exploring unsorted databases and Shor's algorithm for factoring huge numbers may execute jobs tenfold quicker than conventional algorithms. For the next part is quantum cryptography. Quantum cryptography is also consists of two. The first part is quantum key distributions QKD, By utilizing protocols such as BB84 and E91, two parties can exchange a secret key while maintaining security that is ensured by quantum mechanics. Attempts to listen in on conversation cause the entangled particles to move, therefore alerting the persons involved. Next, unbreakable encryption. Since the security is founded on the fundamental rules of physics, it is not susceptible to computational attacks of any kind, not even from quantum computers. So, for the last part of quantum entanglement is quantum teleportation. In bracket, transmitting quantum information. So, it also consists of two, which is the first transferring a qubit's precise state from one place to another without actually moving the particle is known as quantum teleportation. Entanglement and classical communication are used in this procedure. Next one is the long-distance quantum communication, provides the foundation for a quantum internet by enabling the creation of quantum networks in which data may be instantly sent across great distance. That's all from me, thank you.
Okay, so the conclusion is the EPR paradox and quantum entanglement reveal the surprising counterintuitive nature of quantum mechanics. Despite initial skepticism, experiments have confirmed that entangled particles exhibit instantaneous correlations supporting quantum theory. This understanding is fundamental for advancement in quantum computing and cryptography, reshaping our grasp of reality. Thank you.